Okay, I'm going to do yet one more battery power measurement. But this time we're going to have the function generator reference connected to the correct point in the circuit. That is TP8 here, as opposed to TP5 over here where it used to be connected. So now, if there is any current flowing through the MOSFET Q2, through the function generator, we are going to capture it on the CSR1 here as it goes up and around through the battery and around the circuit. Okay, so hardware wise you can see I've made the change right here. Here's the negative terminal or reference lead of the function generator. Now it goes through my 1 ohm CSR to the MOSFET side of the CSR rather than over here where it used to be. Okay, you can see the solder point here where I used to have it soldered. So it's now soldered over here. So the first battery power measurement I'm going to do here is how not to do a battery power measurement, and that is I say not because for two reasons. One, our CSR probe tip and probe reference is got a whole bunch of inductance, parasitic inductance in between the measurement points here and here. So I've got this length of wire, and this length of wire here is introducing parasitic inductance, which is going to skew our CSR voltage measurement. So the other reason is actually because our Vbat measurement is over here. Now this really, in my opinion, is not a V battery. Okay, the reason, because you see this red cable here, it's going through about 8 feet of wire and then eventually gets to the positive terminal of the battery. So there's a fair bit of inductance in this loop here as well. So we're not really measuring the battery per se. Okay. Alright, so let's hook up the power here and have a look at our scope. So the yellow is our current trace, our CSR voltage trace. The red, as usual, is our math trace, and the purple down here is our battery, V battery trace. And let's have a close-up of the numbers that we're getting. Notice the mean of the CSR is about 108 millivolts, and our mean of the battery is about 37.3, 37.4. You crunch that out, you're going to get pretty close to 4 watts. Okay. Have a look at our mean Pbat computation by the scope. It's kind of bouncing around a little bit, but it's showing a positive 0.2 at the moment. Now, let me just move the CSR probe around a little bit. And now it's reading negative 0.8 roughly. Okay, all I did was just kind of rocked the probe. Not sure if it's just a bad connection or what. I think it is, because it seems to be pretty steady now at negative 0.8. Let's go back and have a look. Negative 0.8 watts. So even if you account for the 0.25 ohm resistor, that's not anywhere near what it should be. You multiply the mean CSR voltage times the mean battery voltage, you get about 4 watts, and here we're only indicating less than -1. Okay, now we're just going to move the probe up tight to the body, the resistor, the reference nice and tight, and we'll move the battery voltage reference over as well. Best we can. Okay. And there's our display now. You notice a bit of a change in the amplitude of the AC oscillations, particularly on the CSR. So let's have a look at our mean values now. So we still have a mean CSR about 108 millivolts, mean battery voltage 37.0. It's dropping a little bit because it is using current. But notice our mean Pbat is now indicating 2.27. It's fluctuating, of course, but it's still low. It should be about 4, but it's indicating about 2.2. But notice that it's a positive wattage now, not negative like it was when we had that parasitic inductance between the measurement points. Okay, next I am going to do a measurement, similar measurement, but I'm going to be using this CSR, and I'll be able to measure directly across the battery. Now, you may have noticed also that I just have small loops in here now for jumpers between the batteries. I've removed these purposely made high inductance jumpers because they skew the measurement. And I've got enough inductance here already. I don't need any more to show massive oscillations in the circuit. So the measurement that we just did, our Vbat, was taken up here at TP3, and the reference was TP5, which is way down here. And our CSR probe was also across here. So we had the probe at TP4 and the reference at TP5. So both references are at TP5, which is right there, the other side, the battery side of the CSR. And we have the CSR probe here, which is TP4 over here. And TP3 way up here, after all this wiring to the battery, is this red coily wire here, and there is our TP3 battery measurement. Okay, so I am going to be moving it over to the battery, and we'll see what our Pbat measurement is then. Okay, let's have a look at what's going on over here. I now have the CSR probe connected directly across the CSR, right off the negative terminal of the battery. Okay, it's the same value as the other one, 0.25 ohms. And I've got our battery measuring probe right here in the end of the chain. It's a 36 volt, 3 12 volt battery chain. So here's the positive terminal where I have the probe, and I have the probe's reference tied to the negative terminal of the battery. So we're measuring directly across the battery string with just 2 short jumpers in between. Okay, so our circuit looks a lot cleaner now because we have no measurement probes over here. All I have to do is connect the power, and we'll see what our waveforms look like. Okay, here we are. Now, first thing I want you to notice is look how clean that Vbat measurement is now. Almost no noise there at all. Okay, and the CSR oscillation is probably about the same. But let's have a look at our mean values once again. Okay. Now we still have about 110 millivolts across the CSR and about 37 volts on our batteries. So you multiply that out, it's going to come pretty close to 4 watts. Well, look at that, our Pbat in red. Just under 4 watts. Exactly what it's supposed to be. And just for verification, I have 2 meters connected here as well. So I've got my battery voltage, 37.4. So it's a little bit lower than what the scope is saying, or well, the scope varies, so it is bouncing around a little bit, but it does look a little bit higher, so 37.4, 0.2 or 0.3 volts off. And I have my input current right across the CSR, 107.2 millivolts. And the scope is measuring about 110. So they're pretty close. Pretty darn close, I'd say. So I'm willing to bet that this computed power by the scope is actually pretty accurate. And that is how to do a correct battery power measurement on this type of circuit. So what we want to do is minimize the inductance in the battery links, the battery jumpers, because that skews the measurement, and try to go directly across the battery with our probe. And because we have our probe way over by the batteries, we also need to have our CSR here as well, because our references need to be at the same point. So here's our 2 references right here, pretty much at the same point, okay? And I'm right tight against the body of the CSR. So that's the correct way, the proper way to do a power measurement on this type of circuit. Again, look how clean that battery voltage is. Okay, and those mean values are accurate. And note that they didn't change. No matter where we put the probes, those mean values here, these 2, the CSR and the battery, didn't really change at all. The only one that changed was the math trace. And that's because it's doing an instantaneous averaging of the instantaneous power measurement. And when you have that parasitic inductance everywhere, it throws that measurement off. And that's why it's not correct. And that's why trying to do a power measurement way over here on the other side of 20 feet of wire for your CSR, the CSR is probably not so bad as long as you are right tight in the body, but the battery voltage needs to be taken as close as possible to the battery over here. And the only reason that we can't use this CSR when we're measuring the batteries directly is because we can't put the references at the same place. So that's why we had to install a second CSR over here by the batteries. Okay.